I had to turn it on. Now I understand. It's a hardware thing. I'm totally software. Okay. So for approximately the next 50 minutes, I'll be talking about metadata, primarily metadata in the database in the format of constraints. And this is what we're going to be really discussing. Did you know that the optimizer uses, in addition to statistics on a table, extended statistics? These were new in 10G and 11G. I could gather statistics on expressions in 11G. I could create a SQL profile, which was extended statistics in 10G. System statistics, data dictionary data. How big is the table? How many segments is it in? What is the partitioning scheme? The query plus all of the constraints against the table. That's the inputs into the optimizer. You probably know how bad the cost-based optimizer would behave if you gave it no statistics. It would just assume defaults for everything. We gather statistics to give the optimizer information. We've given you the ability to gather additional new statistics in 11G to give the optimizer even more information. But a piece of information we frequently do not give to the optimizer is this metadata called constraints. Constraints are not just about data integrity. In a transactional system, your HR system, your finance system, data integrity constraints are primarily for data integrity. In your data warehouse, in your reporting system, in those systems where you're running queries that take many minutes or hours or days, the metadata, the constraints, are not necessarily about data integrity. They're about achieving performance. If the optimizer understands how your data model fits together, how the tables relate to each other, the rules that are in place, it can use that to come up with more efficient access paths. So we're going to take a look at a couple. The first integrity constraint I'm going to look at is one that most people don't consider an integrity constraint or a constraint at all, and that's your data type. Your choice of data type is pretty important to the optimizer. I have a saying, wrong cardinality equals wrong plan. Whenever the optimizer comes up with the wrong query plan, a query plan that, for example, if I threw in a hint, it runs much faster, the root cause of that will come back to the optimizer incorrectly estimating a cardinality for some step in the plan. It thought this subquery would return 50,000 records. Instead, it turns out that subquery returns 5 records. There's a huge difference between 50,000 and 5. If I see 50,000 records coming out of a subquery, I might start full scanning, stop using indexes. If I see 5 records coming out of a subquery, I'll come up with a completely different query plan for something. So anytime we get the wrong estimated cardinality, we stand a really good chance of getting the wrong plan. The opposite of this statement is true as well. Right cardinality or correct cardinality equals the correct plan. Anytime we get the correct cardinality, the optimizer is pretty much dead on coming up with the right way to approach that. Here's an example. I have a date field. I'm going to store a date in there, a day, a month, and a year. I'm in a data warehouse. How do most people, or many people, store a date in a data warehouse? Do they use the date data type? No, that would be too easy. They use a character string or they use a number. And into that number or string, they take the date information and they format it in a manner that sorts and can be used in range scans. They'll store it with YYYY MMDD. So here I've created a table where I'm going to go against all objects, about 50, 60, 70,000 rows depending on your version. And I'm going to start with the date January 1st, 1995. And in the outer query, I'm going to just add row num to that. So that's going to generate between 50 and 70,000 unique dates, put them into a table. I'm going to store that once as a date. I'm going to store it again as a character string using that format. I'm also going to store it a third time using a number. Then I'm going to have some other data associated with this. These are our other columns. Now we're interested in querying based on that date. So I'm going to create indexes on those 3 columns. So everything's fair here so far. It's unbiased. I have the same information in 3 columns, represented in 3 different formats, but all meaning the same thing, all indexed, and really good statistics gathered. The best statistics possible, the most information that I can give the optimizer here. Now I'm going to ask a very simple question of this data. I would like to get all of the rows out of this table where the string format of the date is between those 2 strings. You and I look at those 2 strings, and our brain automatically converts that into December 31st, 2000, January 1st, 2001. How far apart are those 2 dates? They're right next to each other. We know that. The optimizer doesn't know that. Down here, the optimizer guessed 254 records. Why does it guess 254? Because we know there's just 1 day between those 2. It guessed 254 because between those 2 strings, there's a lot of possible strings. Strings are not dates. So let's use the number. We'll use the number type because a lot more people use the number type than the string type to hold these dates. Same result. Between those 2 numbers, there's lots of possible numbers. In fact, if you ran this example in older releases of Oracle, say version 8i, or I believe the first release of 9i, the estimated cardinality for the number would have been about 254. The estimated cardinality for the string would have been 2 or 3 times higher. What happened in version 9i was the Oracle Optimizer developers realized that a lot of people hide numbers inside of strings, and the optimizer was changed in 9i so that any time we looked at the inputs to the query, I have 2 strings, and we looked at the statistics gathered, if all of those strings could be converted to numbers, the kernel developers decided to say, I bet you the developer is playing the old hide a number in a string trick. I'm going to pretend that these are all number statistics because all I see are numbers all over the place. And so they corrected the estimated cardinality if this had truly been a number. But it's not. It's a date, hiding in a number, hiding in a string. And there's no way they're going to be able to play that old, oh, you hid a date and a number in a string trick, because there's just too many ways to represent a date hidden inside of a number. What happens if we query this using a date? It's very interesting. I needed to go to a smaller font because the query plan got larger, because the query plan now includes an index range scan, table access by index row ID. This is just a quick demonstration of how this can affect your query plans. For such a small range of data in my data warehouse, I want to use an index on this. If, on the other hand, it overestimates how many rows it's going to get, it will full scan. This could be the difference between a query completing in a couple of minutes and a query never completing in our lifetime. Think of the regular data warehouse queries. They're not simple one-table things. There are 5 table joins with 15 layers of nested subqueries. You get an estimated cardinality wrong at the lowest level, and that just multiplies itself all the way up through all the steps in the plan. So using the right type gives the optimizer more information. It's not only a data integrity constraint, it's impossible to put February 29th, 2001 into the date column. It's completely possible to put February 29th, 2001 into the number or the string. So it's not only a data integrity constraint, but it helps the optimizer interpret the statistics correctly as well.